gitme optimizasyonu akıllı dokümanelerde. Akıllı dokümanenin tanımını birlikte dinleyeceğiz. Daha sonra sorularınızı İngilizce veya Türkçe ekranda sohbet şeyine yazabilirsiniz, kutusuna yazabilirsiniz. Onları Mr. Korea'ya sorarak sohbetimize devam edeceğiz. Good afternoon, everybody. This webinar is organized by Turkish Founderman Society and its training organization, TÜDOKSAT Academy. And we are very pleased to host Mr. Alberto Montenegro Correa from AMB Solutions from Spain. And he will present us a very interesting topic, melting optimization in Smart Foundry 4.0. I asked Mr. Correa first, what does Smart Foundry mean? And then other topics. The content of the presentation is quite informative, but still we will have some questions. And I ask you to write down your questions into chat box at the end of presentation. It will take about 45 to 50 minutes. Then we have got until 90 minutes. We have got time to answer those questions. Mr. Correa, first, could you introduce yourself briefly and then start presentation, please? Thank you.
Yes, of course. Thank you very much. Well, good afternoon, everybody. First of all, thanks to the Turkish Foundrymen Association for letting me participate in this webinar. So I hope that you find it of your interest, and at least that I am able to present some new topic that is of your interest. Well, I will be very briefly introduce myself. My name is Alberto Montenegro. As you know, my background is that I'm a mathematician. I have been working teaching mathematics for 20 years. And in 2008, I started the adventure of applying the mathematical optimization methods to the industry, and very particular in the foundry industry. So I founded the company AMB Solution. I'm currently the CEO. And basically, AMB develops and implements optimization system for the foundry industry. We have customers worldwide in 4 continents and more than 12 or 40 countries. And we are more and more specialized in this sector. Okay, we, let's say, that bet for going very deeply instead of covering a lot of sectors. We prefer to go directly to the foundry sector and try to help as much as we can. So if you let me, I will start. So melting optimization in a Smart Foundry 4.0. So Mr. Sheffi started with a good question, what a Smart Foundry is. Okay, so I will try to summarize what we understand for a Smart Foundry. First of all, as you know, 4.0 refers that we are now living the 4th industrial revolution, that beyond using the automation, computer and electronics that correspond to the 3rd industrial revolution. So we are already using cyber physical system, Internet of Things, big data. So what we want of the systems, they are intelligent and they help us to improve our processes. So considering that, a Smart Foundry is a foundry that implements system that integrates all the devices so that automatically we get and we collect data real time. And with this data, we have a brain, okay? A brain that is, of course, a system that is detecting variations and making decisions and making suggestions so that we will make the most of our resources and of our production. This is, I know that a very high level idea, but I hope it will help. So usually when we start talking about Industry 4.0, there is a question. This is a small character, it's called Little Philip, that is wondering himself, but what if before starting what we must do, we start what we should have done? So before facing 4.0 industry, we need to make us some questions. So how is my 3.0? That means, do I have my devices, my spectrometer, my scales connected to the system so that nobody is manually typing anything and I have a reliable information? Second, did I identify the processes that I can improve? Okay, probably. First, we need to ask this. Also, have we analyzed which tools or which techniques can provide support to implement? And of course, and this is very important, what are the potential benefits of applying such systems, okay? So we will try to give response to these questions, okay? Processes, techniques, and benefits. We are going to analyze these three factors. And the idea, we are going to focus this webinar in the application of these techniques to the melting process from the raw material purchase until my metal is ready to pour. So how we can monitor, control, and optimize all the processes until we have a good quality metal. Okay, there we go. First, I'm very briefly will introduce the techniques. So from the mathematical point of view, okay, we have the operational research algorithms. Those algorithms are intended to find an optimal solution for a given problem, okay? And those algorithms will detect the optimum, and if there is no solution, so will inform, or if there is no optimum, will inform, okay? Will give a very accurate response, and very often, at least for the foundry industry, in a very short time. But when things get a little bit more complicated, because the number of feasible solutions is huge, and there's no chance to analyze all the space of solutions, or because we want the tool also to analyze patterns, to predict, to correct, to detect issues, so we need to go through the artificial intelligence. In the case of artificial intelligence, they use techniques that are based in heuristics, theoretically human heuristics, okay, that very often simplify the space of solutions, so that if we don't get the very optimal, at least we get a very good solution, okay? So let's say this complement when operational research is not applicable, so we have the artificial intelligence. Sure, you heard about machine learning, and we will talk about it a little bit later. And then also, sure, that very well known is the statistical process control, okay? We have statistical variables that give results in terms of probability, and we want to set the relationship between them so that we are going to use those three different techniques in order to optimize the melting process. So this is the point, okay? What we need, OR refers to operational research, artificial intelligence, and statistical process control. What we need to do, of course, is model all those techniques with the foundry requirements, okay, and with the melt shop's requirements, so that we optimize the raw material costs, the energy cost, and the process time, okay? So the analysis that we will be making is in terms of how much I save in raw materials, how much energy I save, and how much time I reduce and increase my productivity. And the good point is that, okay, sometimes when one think about optimization, cost reduction, immediately some people think, okay, my quality is going to drop down. But this is on the contrary. We are talking about control so that my resources and my costs will drop down and my quality will increase because I will have a much higher control of the whole process. Well, which processes are we going to analyze that we consider critical when we want to optimize the whole melting process? Of course, the first one is the raw material purchase. If I'm not efficient in buying raw material, okay, my costs are not going to be good, of course. The heat scheduling is also critical. We will analyze the heat scheduling. Then there is a point, okay, I have a good schedule of my heats, but I want a very efficient recipe. I want to save with my recipes when I'm going to melt one alloy. A very forgotten point is the melting follow-up. I think that this is very important. I will talk about it. And then, of course, at the end, when we accumulate data, use this data for data analytics. 4.0 is very linked to big data. And sure, most of you have heard about that. And sometimes the complaint is always the same. Okay, here's my data, and what do I do with my data? Okay, I have now hundreds of thousands of millions of information. What do I do? This is something that we are going to, at high level at least, analyze. Let's go with the raw material purchase. For the raw material purchase, the inputs of the problem are my production needs. So I need to cast this alloy and this other alloy with those quantities. This is my current inventory of raw material. Okay, I have in my warehouse this scrap, this return, those ferroalloys, etc. And I have some quality constraints, of course. And in front of that, the market offers me scraps and virgin material with some prices. So I think that it's quite easy to understand that for a human brain, dealing with that information together and figuring out what the optimal solution is actually an impossible task. The good point is that here we don't need very complicated techniques. So in the case of the foundry industry and in the case of the volume of information that we need to handle for the foundry, with operational research algorithms is more than enough. And what these operational research are going to give us when we deal with the purchase is my optimal raw material purchase. So I should buy this amount of scrap 1, this amount of scrap 2, and this amount of nickel, and this amount of whatever, okay? And what is even better, I will have elements for negotiation with the scrap dealers because I will have an objective value, not price, but value of the raw material that they are offering to me. Well, we have a lot of experience in this field, and it can be surprising, but we have detected typical ranges of cost reduction in the raw material purchase between 4% and 12%, okay? At the end of the presentation, we will analyze how much money this represents. But of course, we have even higher than 12% and in some cases lower. The complexity of the production, the complexity of the alloy specification, the number of, the complexity of my inventory will determine what if I will be closer to the 4% or closer to the 12%, okay? I will anticipate that, for instance, if we think in ferrous alloys, for the ductile gray iron, the range is closer to the 4%, and for, let's say, alloyed steel, we will be very close to 12% or even higher. Well, so the second point is the heat scheduling, okay? I have my work orders, okay? I need to cast these part numbers for this customer, this for the other customers. Of course, I committed to give and to delivery on time. I have molding constraints. I have melting unit capacity constraints and some compatibilities. Okay, I need to analyze if I can cast in the same heat and in the same furnace this part number with this other part number together, or I need to separate. So this is processes very complex, so that in that case, a good heat scheduler only based on operational research wouldn't give feasible solutions in a feasible time, okay? So in that case, we need to analyze also techniques of artificial intelligence. For instance, to optimize the sequence of the molding together with the sequence of the heats. Okay, we need to use artificial intelligence techniques, and also to maximize the usage of the furnace, and also to learn about what happened in the past. Okay, because my operations take a time, and I want this knowledge in a continuous improvement. Okay, so that as I accumulate a history of data, my knowledge will be more accurate and my scheduling will be more accurate. In that case, for the scheduling, if we have a good, let's say, a sequence coordinating the different areas, the impact in energy is very important, easy to understand, because I make the most of my furnaces and I reduce the time of the operations. And of course, I will increase my capacity, and probably we will be talking about time reduction between 5% and to 10%, okay? We are talking also about the difference between an intelligent, smart system compared to a high qualified operator, okay? The third point, charge optimization. I'm sure that many of you, if there are foundry men there, then sure, and I hope they are, you know that to get the same specification, we can use very different recipes. Sometimes my inventory of returns has more of one material, other times of other material. The raw material prices are continuously changing, so the recipe that was effective 2 months ago is not effective anymore today. So this is the point, okay? And here also we have good news in the sense that with operational research and in very short times, I would say that immediately, okay, considering my inventory, my charge constraints, and my alloy specification, we will be getting the least cost charge for a single heat or for a complete campaign, okay? So that with that inventory and that production, okay, this is the best, the optimal way to split the different scraps and the different returns between the whole heats and the whole production. In that case, if I optimize my purchase and I also optimize the charge calculation, I can add an extra 2-4%, so that in total we would be reducing my raw material cost between 6% up to 16% or so, okay? Also energy savings in the sense that I will be reducing, if I have an accurate system with a good chemical balance, okay, I will be more often, right first time, I will reduce in the number of chemical correction, and that will result into an energy savings. And of course, for the same reason, in process time reduction. Okay, let's go to the fourth point, that this is the melting follow-up. Very often we think that the expert systems and the intelligent system are only aimed for engineering department, purchase department, quality, okay? And then the poor furnace operator is left alone with a paper, with a recipe, okay? And needs to improvise. Sometimes there are things that are not expected, and he needs to improvise because, okay, I don't have enough scrap of this quality, or the format of my return is this, so what do I do? The idea here, and we at the end will show a real case study, is to build what we call an ecosystem. This ecosystem includes the integration with scales, spectrometers, if possible automatic charging system, okay? To also to provide a real-time control of the melting units, and also allocate terminal computers accessible, reachable by the operators, by the furnace operators. The actions that are supposed to be performed is what we call the charge recalculation. When I am collecting the charge, okay, there may be variations in terms of the recipe and the actual quantity. So if I don't correct the remaining charge as the process is live, what will happen is that there will be variations from the theoretical chemical composition and the final one, and also in terms of volume, okay? I want 2 tons of CF8M, okay? So this is what I want, and please, while you are collecting the charge, try to adjust to this requirement. Also, when we need to simulate the metal flow, sometimes, for instance, for aluminum recycling, can be quite complicated because the same metal moves from one melting furnace to other melting furnace and then to a holding furnace. So we need a system that knows exactly what is happening at each furnace, okay? And where the metal that is in the heel of my furnace come from. And of course, then needs a system that automatically says, integrated with the spectrometers, what's the optimal correction to be in spec at the end. Well, as a result, if we follow up the melting process with an expert and, of course, a user-friendly tool for the melting operators, we will have a higher control of the required metal, okay? So we can reduce the need of extra safety amount. Yes, this is one part. The second part, that my chemical accuracy will improve because I have a higher control during the collection, the charge collection process. And what is very good, I will be storing a reliable data for data analytics, okay? Because nobody will be manually input a weight, nobody will be manually entering a chemical composition. All this information with our ecosystem will be imported from the different devices. As a result, less rework, the number of chemical corrections will dramatically drop down, and better chemical consistency, which sure the customers of Foundrymen will love. What this aspect affects to everything. First, there are also the raw material savings in the sense that if there is any unexpected issue, the system recalculates the optimum real time. Energy savings because of the same reason, because of the drop of chemical adjustment, and process time reduction also because we will be much more often right first time. And to finalize, the 5 processes that we are going to control are data analytics. Okay, let's say that our system obviously use inputs, okay? If I want to get a least cost charge, someone or somehow the expected chemical composition of each scrap and the recovery of each scrap should be into the system, okay? But what happens if I accumulate a history of what was with this charge, I get this chemical compositions, with this other charge, I get that chemical composition, I experience those melting losses, etc., etc. So the idea here is applying both techniques, statistical process control and artificial intelligence. That means that with all that data, I will be able to estimate and predict the chemical recovery by element, raw material, furnace, and operation. Okay, so my knowledge of how the scrap of this provided performs in this kind of furnace or that other kind of furnace will improve in a continuous way. Okay, I will be able also to analyze the deviation between the expected and actual chemical results, because if the system calculates theoretical charges and give me some expected results, if the calibration is good, and if my machine learning process is also good, these results, the theoretical and the actual ones, should match more and more, and this is the point, no? And then the real-time correction of chemical inputs. Sure that if you are foundryman, very often you were expecting some results that sometimes the content in chrome increase higher than expected, or my sulfur, or any residual. So we need a system that detects and autocorrects. Okay. It affects directly the energy savings. You have estimated between 2 and 4%, depending on the complexity, and also it will affect my process time reduction. Also because at the end we will be reducing our rework. Okay. Well, if we go to the overall improvement, we are talking about a potential savings between 7 up to 17 in raw material, almost 8% up to more than 15% in energy, putting everything together. Okay, if we optimize every one of these processes, and also a production time of more than 10%, that means that here we will be much more productive and, in short, much more competitive as well. In terms of savings, okay, based, for instance, for energy, for a typical energy of 600 kilowatts hour per ton, okay, and for a typical energy cost, here we are, okay, the figures are expressed in euros. If you multiply this more or less by 9, it will be converted 9 or almost 10, it will be converted into Turkish lira. So assuming this information, we have detected that for each 1,000 melted tons, okay, we can save more, or almost 4,000 euros. And we will be increasing our productivity in terms of melting in more than 13 hours, each melting 1,000 melting tons. If we analyze in terms of cost reduction, okay, here we have classified, for instance, cast iron or low carbon or low alloy steel, the stainless steels, duplex, super duplex, or the aluminum, okay. So typical savings for each 10,000 net tons, okay, that can be a production for 1 year for some. Okay, let's use this as a reference, okay. We can be talking for cast iron of total savings of 300,000 euros a year, okay, and an increase of productivity of more than 200 hours. In the case of stainless steel, because of the, let's say that the raw material is more expensive and the complexity is higher, we can be close to €1 million a year, okay, 900,000 euros with the same increase of productivity. And if we talk about aluminum, okay, well, in this case, assuming a yield higher, okay, if you say check here, we accept a yield of 60% for aluminum and stainless, and for cast iron and stainless steel, 95%. Of course, we can change these figures, but at the end, the important thing is that if we apply smart foundry techniques and big data techniques, so those are typical figures. Okay, and just to finish, because so far the presentation has been, of course, based on our experience, but in theoretical terms, we will present a real case study that we performed in United Gas Bar, Chesterfield, UK. Okay, so very shortly, United Gas Bar is a foundry that produces gray and ductile iron bars in a continuous casting process. They use 8-ton induction melting furnace, and let's say that typically one bar, okay, can be will require at least 2 or 3 heats, different heats, because of the final weight. So that chemical consistency is critical, because it wouldn't be very nice if I deliver to my customer a bar that has a chemical composition in one extreme and a different chemical composition in the other one. It wouldn't be very, very nice. So for them, the chemical composition is critical. So the need was to improve the chemical control and optimize charges and minimize corrections. The minimize of correction, that's why the project was called the right first time, as I indicated here, okay? Is, let's say, melt and tap, no corrections. This is in the ideal world, of course. So the start situation was that having a good history of data, they didn't have a specific tool to deal with that information. The charge calculation system was Excel-based, okay, with manual changes of some operators that, of course, not the optimal in the sense of getting the least cost charge with chemical composition. In terms of registry of the production, they registered the weights and the chemical composition, but all the values were entered manually, so that the history was not very reliable actually. And at that moment, at least 72% of the hits required as minimum one adjustment. This was the start situation in October 2017. So first actions that were performed is that we proceed with the implementation of the ALEA system with the capability to optimize the charge, to recalculate the charge during the collection process. This is what I mentioned in point 4, no? That, okay, it's not only if a recipe, is follow up the process to recalculate if required. And they use the system to optimize also the adjustments. We integrate the whole scales, the crane scale and the platform scales, and we also integrate the spectrometer. So let's say that the layout was this. Let's say that ALEA acted as a core for collect the information from the crane scale, platform scales, a spectrometer, and provide best solutions to charge the furnace and also to adjust the chemical composition. Okay. Here in this video, you will see the screen for the crane operator. So if you check, he receives the optimal recipe on the screen. Okay, of course, they use Wi-Fi connection. And in that case, I will stop. Let me stop here 1 second. If you check here, the recipe consisted on 5.5 tons of pig iron, and the actual one was only with an error of 18 kgs. What we can say that it was almost exact. Okay, and it could be by chance, but at the end, with a second scrap, you will see the difference. Okay, so on the right side, the system is storing each drop. So even is storing the user, the crane operator, how much material was charged in one drop. Okay, and again here you can see how the difference between the recipe and the actual charge was minimum. Okay, so this was critical to accumulate a reliable history and also to use accurate values. So the results come very quickly. After 3 months of use, just with initial recalibration, the number of chemical adjustments dropped down from 72 to a half, 36, and then in June 2018 to 31. Okay, but so far we hadn't performed data analytics. So after that, in June, what we did was collect this reliable history, okay, and analyze the data for the last 2 months. So in that case, we only applied at this moment a statistical process control so that for each raw material and each chemical element, we got the confidence interval, so that, okay, your manganese for this scrap must be in between 0.4 and 0.6 with a probability of 95%. What we did at that moment was detect that those chemical inputs that were out of the confidence interval and moved into the closer into the confidence interval. That means that we used this analysis to improve the inputs, and when we improve the inputs, the hypotheses were that our charge would be more accurate. So here, well, it's not very easy to see, but here we have the red triangles represent the actual chemical composition get from the spectrometer. The yellow values represented the expected values of ALEA for the same heat and the same chemical element, in this case carbon, before performing the statistical process control and before recalibrating. And if you see, and the green small circles represent the expected values after the recalibration of the system. So even though it's not very easy to see, at the end, the expected and the actual values after the data analytics were much closer. But the good point were the results in production. So if you see here, we have two graphics, okay, and two milestones. These milestones represent the implementation of the ALEA system. And these milestones represent the start of using the data analytics with the history. So we move from the 72 to the 36. And after performing the recalibration, we drop down to 20%. Only 20% of the hits required one adjustment. And what is even clearer, if we talk about second adjustments, it moved from the 4% before ALEA, down 1% with the ALEA implementation, and since they started applying data analytics, no more second adjustment were required. Okay, so as much, 20% of the hits required an adjustment and never a second adjustment. In terms of costs, okay, with the number of hits per year, assuming that each chemical adjustment required extra 11 minutes, with this power, okay, 3.5 megawatts, and this price in terms of British pounds of each kilowatt hour. So this represented at the end of the year, only in terms of energy savings, more than 130,000 pounds or more than 140,000 euros a year, and a process time reduction, a melting process time reduction of more than 150 hours a year. Okay, so I think that results are quite clear. So just to finalize, just highlight the importance of the application, okay, of operational research, artificial intelligence, and statistical process control to implement a system that handles this technology. The importance of the real-time monitoring so that the furnace operators also have access to a system and that can use to recalculate during the melting process. And so at the end, the impact in the cost, okay, in a market that is more and more competitive, may have an impact of the same order or higher than the commercial margin. This may happen. This may happen that I am losing the same amount of my commercial margin, or even if my competitor use these techniques, okay, we have this margin, competitive margin compared to me. Okay, so this can drop me out of the market. So it's very important. And of course, now, if we analyze the global scenario of COVID-19, okay, and many with the drop down of the production, there are a lot of companies that are taking advantage of the time, okay, to improve their processes and to search for systems that help them to face the new market, let's call it like that, a new market in most competitive conditions. So thanks, that's all in terms of the presentation. Only just let me remember this is myself in case you need the contact, okay. Our representative in Turkey, Doğuş Metal, okay, with Dr. Özgür Çelik. You have also those details. And I also introduced, okay, a new system that is, if ours is Alea, this is beyond Alea, in which we are introducing machine learning techniques, okay? So depending on the modules that each foundry want to use, sometimes with the Alea is enough, and other times we need to add modules of the beyond Alea. So thank you. So please, I hope that I made myself a little more or less clear, and please, I'm open to any questions that you may have. Hello.
Thank you, Alberto, for your very valuable views and results, actually. Your live result coming from foundry industry for the case study coming from steel casting, iron casting foundry.
Yes.
Is there a similar case from aluminum industry? Have you got any success story from aluminum industry?
Well, we are starting applying now for the aluminum industry. In fact, we are now focusing in the big steel making plants and the big aluminum recycling plants. And we are now with 2 implementations that include the whole package, okay, with the machine learning module. The results are being we are getting very, very good results. And let's say that we have more and more big aluminum plants interested in the system. Now, yes, we are the closest to you is one plant in Greece, okay, that they produced aluminum slabs and rolling from scrap, and let's say they're very happy. We are in the implementation process, but they tested the system for 8 weeks with excellent results, no?
According to your experience, how long does it take to get a clear view of a plant to apply Alea in this plant?
Okay. Let's say it depends on the modules that we implement, okay? But for instance, if we go to the layout that I presented for this cast iron foundry, it took us, we implement for 1 week, okay? They started using 2 weeks later in production. We came back 1 month later after the first visit, and so at the end it was 1 month. In 1 month they were fully operative. If we're going to implement machine learning, so probably after we would start from the beginning, but probably would be getting good results in 2 or 3 months. If the scope is less, that means that if I only want to integrate my scales, my spectrometer or chemical analysis, I'm a raw material inventory. So let's say that implementation typically is 1 week, and in 1 month is fully operational, the system.
Thank you. Thank you. When I look at the chat box, there isn't any question there. Just as they are saying that thank you for the presentation. Do you want to say something extra to your presentation? Because there's no question for the moment. If there is, they will raise their hand.
Okay. No, just, well, let's say that the presentation goes focused, no, in the scientific and technical point of view. The important thing is that, well, of course, this is a teamwork, okay? That means that in each case and each implementation, there is a team on A&B side, and there's also a team on the customer side, okay, a project manager. So if working in this direction, normally the results, we usually make a return of investment analysis. No, in this return of investment analysis, they provide us the raw material inventory, the alloys that they use, the type of furnaces. We predict some savings, and in general, the final results are even better. No? And also, just from my point of view, is that you have our details there. In case you want to contact us or you want to contact Dogus Metal, we would be more than happy to make a practical presentation. Okay, in a practical presentation, you will understand how you can handle each part of the processes with the system and how the results are. And also, of course, that if you want to see current customer success cases, so you feel free to access our website. Okay, so okay. That's all on my side.
Yeah, Alberto, there is a question from Cengiz Eren, one of our participants. He's asking, what was the difficult application at Chesterfield Foundry?
The difficult.
Yes.
Yes. I understand that the difficulties that we faced in Chesterfield. Well, I would say that not too many, because the plant director involved himself in directing the project. So probably the difficulties that we faced at the beginning, some connectivity issues. So they need to try a couple of different ways to integrate the crane with the network, but after that is working very good. Well, from the training point of view, actually maybe that it took a couple of weeks that we trained the super users, and then the Chesterfield super users trained their operators. So at the beginning, quite often there is a small resistance to new technologies. So this is one other difficulty, that you need to convince that this is an improvement. And at the end, they love the system. That means that, I don't want to do like this. But after 1 week or couple of weeks, it's like, no, I don't want to come back to the previous scenario. So I would say these 2 points. Some issues, connectivities that need to analyze a couple of technologies, and then the initial resistance of some operators that are not very used to IT. Okay, no more than that.
Okay. One more question coming from Emrah Gençal. He's asking, do you add load cell to central melting furnace to weight the metal inside if it's an old type furnace?
Sorry, of course, can you read it again, please?
Do you add load cell to central melting furnace to weight the metal inside the furnace if it's an old type furnace?
No, well, good question. We'll have a partnership. In fact, the Beyond Alea system is developed with them. with a furnace manufacturer in Bilbao, so that the system is automatically integrated. In fact, it works as an only system. So we collect waste, we collect temperatures, we collect times and everything. And with other type of furnace, we make a one-by-one analysis. If normally we use what is called like a passerelle that integrates the industrial network with the data network, okay? So it requires, we also have partners that can do this work, okay? So with our partners, the integration is automatic, it's a default of the system. And with other partners, we make a one-by-one analysis, and we can also provide the integration, the physical integration.
Okay, one more question from Cengiz Eren, the owner of the first question. How many foundries have been using your system in Europe?
Well, in Europe, I think that there are 20 something. I cannot say. We have so far 45 worldwide. Okay, fortunately, growing very, very, very quickly, and half in Europe and the other half out of Europe.
I forgot to tell the participants that this presentation is already recorded and accessible in TÜDOKSAT Academy website. If you want to watch the presentation once more, that is available. It seems that is all from the questions point of view. No more questions. And we thank you once more for your kind presentation, very valuable info, what you have shared with us, and hoping to see you sometime in Turkey in different media, like in our congresses.
Yes, yeah, no, thanks to you, thanks to all the people that have been attended. And yeah, of course, before COVID, we were supposed to attend your, I think that it was in October or November, I'm not sure.
In November, at the beginning of November.
So, yes, we canceled our attendance in this scenario, but it looks like it's been postponed, no? For 2021.
Postponed to June next year.
Perfect. So if everything evolves in the good direction, we will meet it was in Istanbul, isn't it?
Istanbul again, yes.
Istanbul.
Yes.
Okay, so so I will also enjoy your Istanbul again. Last time that I was there was as a tourist, and now it's going to be in a different way. Yeah.
Okay.
So
thank you.
Thank you very much. And any questions, you have our details there.
Yeah. Okay. Thanks. Have a nice day. Bye bye now.
Thanks. All. Same to you. Bye bye.